We have the next talk, a little bit shorter, about how our liquid crystals like geometric packing problems by Jonathan Selinger. Looking forward to it.
Thank you, Mr. Chairman. Thanks to the organizers for the opportunity to speak out here. Yes, I would like to tell you about how liquid crystals are like geometric packing problems. In this talk, I am going to begin with a quick introduction to liquid crystal physics for any of you who might not be familiar with that area. And then I'll tell you about elasticity theory and how that leads in to thinking about geometry in liquid crystal physics. So to begin with this quick introduction, right? So liquid crystal, right? So this is a term for a kind of phase. These are phases with partial order. So that is to say more order than isotropic liquids, less than full three-dimensional crystals. They are typically composed of long organic molecules like this. And if we want to take a kind of coarse-grained physical view, we could say, let's represent that as an arrow, right? Something that has a particular orientation in space. And thank you. And then, of course, we have an ensemble of many of these things, like 10 to the 23rd of them. And in the nematic liquid crystal phase, the most common liquid crystal phase, they tend to align with each other, rather like a ferromagnet, but not exactly, because they line up pointing either way along some axis, right? And so it's an order that can be represented by some double-headed arrow like this, okay? So this is called a nematic liquid crystal phase. This double-headed arrow representing the orientation is called the nematic director, represented by a unit vector, with the understanding that n and negative n represent the same physical state. So then we can zoom out some more, and we can say what happens over long length scales, right? That the distribution might have one characteristic axis over here, but some other axis over there. Question?
Can I ask a very fundamental question
Please.
about why? So I've seen crystal talks like this, and they talk about a director field as a vector field. But since the direction doesn't matter, this is really a rank 1 tensor field, isn't it?
Rank 2.
Rank 1, because it's made by just a vector tensor with itself, right? No, we're using different rank. I'm saying that the rank of the matrix is 1, not that it's a two-dimensional matrix, IJ.
Yes.
But the rank of that matrix is 1. Yeah, it's.
I'm not familiar with that.
The dimension of the row space is.
Oh, okay. All right.
So why isn't this treated as a tensor field when the direction doesn't matter?
It can be.
Okay.
And especially if you're concerned about the magnitude of the order as well as the direction of the order, that would be a good reason to think of it as a tensor field with variable eigenvalues as well as variable directions. So yes, that is also done. And there are uses for each type of theory, right? But normally, if you're working in a system at constant density, constant temperature, where you don't want to think about the magnitude of the order, where it's uniform approximately everywhere, then and you have this uniaxial rather than biaxial description, right? Then the tensor, it involves all this extraneous information that you don't want to think about. And so to kind of reduce things down to the minimum, people speak about this unit vector.
But then you have to also guarantee that whatever theory you have is independent of the sign of that.
Yes, absolutely. As I will talk about coming right up. Yes. Okay. So this is where my talk begins, right? With what happens over these long length scales, right? So that when there are gradients of the director like this, right? That will cost some elastic free energy. And the question is, how much elastic free energy will it cost? And if there are different kinds of gradients, what different elastic modes are there to enter into the free energy? Okay, so there's a standard approach for this. And then I have a kind of a variation, a reformulation of this approach that I want to present to you here, right? And so for any of you who are familiar with liquid crystal science, this will be a little bit different. If you're not already familiar with liquid crystal science, never mind, you don't care. But, all right, so the way I want to present it to you is based on this mathematical construction here, which starts with the tensor of all possible derivatives of the director field. Okay, and so this is some 3 by 3 that shows how nx and y and z can vary as a function of x, y, and z. Okay, and there is this construction which breaks it up into 4 different types of mathematical objects, or if you like, 4 irreducible representations of the rotation group. This was actually done relatively recently in the history of liquid crystal science by Gareth Alexander and his student Tom Shun. Is Gareth here? No, we lost Gareth. All right, well, never mind. They did it for a purpose of topology, but here I think that a great application of it is for elasticity theory, as I will show you. Okay, so let me explain. The first mode here, so this is a 3 by 3. It could in principle have 9 components, but because n is a unit vector, there are 3 constraints on it. So we're down to 6 components that we need to account for. 2 of them look like this, okay? And they are called bend, right? So bend represents a director field that goes up and over like that. That's one component. Or it could be up and over like that is another component, okay? So this is a vector perpendicular to the average director. So it has 2 components. So it accounts for 2 out of 6. Okay. It can be represented mathematically as this expression, n cross curl n. This is a visualization. This is like what I was trying to do with my little interpretive dance. And so this is showing a structure that has non-zero local bend, and these other things all 0. Okay, and you can see that the construction of bend has 2 powers of n in it, right? And so it is invariant whether you choose n or negative n, right? So no problem with that issue. Then that's one pair of components. Okay. The next piece here is called twist. Okay, and it is defined as n dot curl n, and it looks like this. Okay, so this is a structure where the director is going back and forth like this, and it's the same all the way around. Liquid crystal people sometimes call that double twist. It has to be the same all around because it is a scalar. It doesn't have any direction. Okay, so this is the visualization of that. And once again, you can see that it's invariant under the transformation of n to negative n. So again, it is there's no sign ambiguity. Okay. Third component is called splay and is defined as the divergence of n. Okay, that represents a deformation that is going outwards like this, the same all the way around, right? So the director in the middle is up, goes out. It's the same all the way around, again, because it's a scalar. It has to be the same all around. it has only one power of n. If that troubles you, you can say, let's just multiply it by another factor of the vector n. And then you get a vector parallel to n, which is uniquely defined. Okay, and so you could say splay is really a vector parallel to n, and it's saying that up is different from down in a picture like that, which is unambiguous. Okay, so we've got two components for bend, one for twist, one for splay. That's 4 out of 6. The remaining two components are this extra mode, which is called delta. Okay, and this is a mode which has not been considered much in the history of liquid crystal science, but it is for sure there. Right, it is a mode that sticks out in one direction and in the orthogonal direction. Okay, and so if the average director is along z, say it sticks out in x and in y. Okay, that's not bend or twist or splay, but it's something. It costs energy, so it's there. Okay, and so this is one component, and then here's another component of delta, which is rotated by 45 degrees. So it sticks out like that and in like that. Okay, and once again, well, so how do you define it mathematically? Well, it's that minus this stuff. It's a little bit messy, but surely not the worst thing I've ever worked with in my career. It is explicitly odd in n, but if we want something that's unambiguous, we can just take an outer product with n itself, and then no problem. Okay, so that's a third rank tensor. Okay, so now for the elastic free energy, it's conventionally written in this way, which is actually a little bit weird, right? It looks like splay squared plus twist squared plus bend squared. And then they've got this other combination of stuff, which is called saddle-splay. Okay, and what I would point out here is that this saddle-splay stuff is equal to a half splay squared plus a half twist squared minus the trace of this delta squared. And so then the elastic free energy becomes a sum of squares, which I maintain is what an elastic free energy always should be anyway. Okay, so this is the form that I like to work with. Okay, so this is liquid crystal elasticity theory. Okay, and it's based on having these 4 modes, which are 4 types of mathematical objects. Now, why do I care about formulating liquid crystal theory in this way? Okay, well, there are several reasons, but the one I want to emphasize for today is that each of these modes can couple to some extra molecular order, which might be present. Okay, for example, let's think about bend. All right, it is a vector perpendicular to the director. Okay, suppose you have molecules that are shaped like bananas, and they have some tendency to order the sideways axis. Right, so in the typical uniaxial phase, the bananas are lining up vertically, but the sideways axis is random. Okay, but suppose some molecules might tend to order the sideways axis in some spontaneous direction. In that case, that would create a favorable bend. The most favorable alignment of the long axes would no longer be uniform, but would be bent in this way. Okay, so you would have a situation where their optimum state has non-zero bend, but 0 splay, twist, and delta. Okay, likewise for splay, right? If you have these pear-shaped molecules, and in the typical uniaxial nematic phase, half are pointing up, half are pointing down, but maybe that becomes unbalanced for some reason. And so you get this population difference that would couple to a splay and create this kind of a variation. Okay, so the optimum state would have non-zero splay, zero everything else. That could happen with twist, right? And so this is something that organic chemists do all the time. It's like make molecules that are spontaneously chiral, molecules that are chiral, they're different from their mirror images, and they have some population imbalance. In that case, there's a favorable twist. Okay. And likewise, for the last case, I'm just kind of making things up here, but yeah, why not? I can say maybe if you have molecules that are shaped like these distorted tetrahedra, they'll have some spontaneous tendency towards the delta mode to stick out one way on the top and the other way on the bottom. In that case, right, so in these four situations, right, we have a liquid crystal that tends to make one of these modes be non-zero and the others all to be zero. Okay, so that's the local ideal state. But then you have to ask, is there any director field that has this local ideal state? Not just at one position, but everywhere in the sample. And in general, the answer to this question is no. Okay, that it is just not compatible with three-dimensional geometry. Okay. And there's been many years of theoretical research which go into this no, which I don't really have time to talk about. But let me emphasize maybe just this work of Virga in the mid, right, who noted that in 3D Euclidean flat space, only certain combinations are allowed that would be homogeneous, uniform everywhere. You can have twist and delta or bend, twist and delta, and that's all. Other things can happen in non-Euclidean geometry, which maybe I'll talk about next week. Okay, so that makes a situation of geometric frustration, right? That there's an ideal local state which cannot fill up space, like a geometric packing problem. Okay, so we can ask, how does a liquid crystal resolve this kind of problem? And in general, there are two ways, right? One is to fill up space with an allowed combination of deformation modes. It can have the mode that it wants, plus some other mode that it doesn't want, but it's willing to accept in order to get the one that it wants. Alternatively, it could break up space into domains of the favored mode, separated by domain walls or defects. Okay, both of these things happen. Let me show you. So first, let's think about the chiral case. Okay, so the case where there is a modulation driven by chirality that makes a favorable twist, but everything else is unfavorable. Okay, one thing that a liquid crystal commonly does in that situation is to make a cholesteric phase. So that's a phase where there is a helix from the bottom to the top. So it's coming around like this, okay, with a certain repeating pitch. So that has a director field given by this equation. And, you know, I can calculate all these modes explicitly, and it has zero splay, non-zero twist, zero bend, non-zero delta. That's one thing you can do. Alternatively, a less common, but still experimentally realizable situation is that the liquid crystal can make a blue phase. So that's a phase that has a bunch of tubes like this, which have approximately pure double twist. Okay, so from the center of the tube going out towards the periphery, the director's twisting around like that. And then the material can form a lattice of these things with cubic symmetry, and that fills up space most of the places, not quite everywhere. And it all fits together, except that there are certain defects where the director conflicts with neighboring sites. And those are shown by the blue lines there. These are disclination lines. So which does the liquid crystal do? Right, they're both possibilities, right? In either possibility, the liquid crystal has the right amount of twist, right? In either possibility, the liquid crystal can have as much twist as it wants. The difference is, what does it have to sacrifice in order to achieve that twist? In the cholesteric phase, the sacrifice is that it has the delta mode, right? Which is unfavorable, but it comes along with the twist. In the blue phase, the sacrifice is that it has to make all these cores of disclinations, right? Which certainly costs some energy per length, okay? So which is worse? Well, it depends on the energetic parameters, right? K24 is the elastic constant for the delta mode over here, and then there's some disclination core energy over there, right? So depending on which of those is higher, that's what the liquid crystal doesn't do. It does the other thing that has the lower free energy cost. So this is a story for modulations driven by chirality. And it's not a new story, but it's a new kind of rationalization of the story, right? Of understanding what drives the liquid crystal to have one kind of modulation as opposed to another. Now, what about the other three cases, just briefly? Okay, so what if there is a modulation driven by perpendicular polar order, right? That couples with the bend, gives a favorable bend. In that case, one possibility is that the liquid crystal could make a helix where the director is not perpendicular to the axis, but at an angle, so it goes around like that, okay? That has a combination of bend and twist and delta, okay? So the bend is energetically favorable. The twist and delta come along for the ride so that the liquid crystal can achieve the bend. Alternatively, there could be a structure like this one, right? Where there's a domain of almost pure bend, and then a domain wall or defect where the sideways banana axis randomizes, and then it reforms and makes almost pure bend the other way, and that repeats. Okay? So those things are known as the twist bend and splay bend pneumatic phases. Those are other possibilities that have been seen. What about if you have parallel polar order? Okay, so the order of molecules that have more pointing up than down. Okay, in that case, you cannot. There's a favorable splay. There's no phase on the menu that has a mixture of splay and one of the other deformations, and so it has to make a structure with domains and domain walls. Okay, and so that could be laid out in a one-dimensional way, like this, where there's splay and then a randomizing wall, and then splay the other way in a randomizing wall. Or the whole thing could be broken into a 2D checkerboard lattice, like this one, or some 3D lattice of hedgehogs, like that. And finally, for my hypothetical octupolar order, represented by a tensor of rank 3, that could stabilize various different kinds of combinations. It could stabilize a cholesteric phase where you would have a favorable delta mode and the twist just comes along. So it could be right-handed or left-handed randomly, or it could be one of these more complicated structures with domains and walls. So with this here, let me just show a table to summarize this whole story. Okay, that there are these 4 different deformation modes. Each of these couples to a type of extra molecular order. And so those make the different optimal local structures, but none of those structures can be achieved everywhere in space. So the liquid crystal has to make some kind of compromise structure instead. And there are a lot of different compromises. And so that's, some interpretation of why liquid crystals have so many phases, right? That there are just so many different ways to make compromise. Okay, so that kind of sums up my conclusions. I've got a couple articles about that if anybody's interested. Thank you all so much.
Great to learn about liquid crystals. I was always waiting for such a talk. It was great. Any questions? Because I have one actually. Maybe let me step before people prepare their own question. When you formulated the energy, there were 4 deformation, and you seem to like take the Taylor approximation of quadratic terms there and sum up quadratic terms. And I'm just wondering, is it not possible to have energy cost, which is, the 2 different deformation terms coming together, the more general? Why are they so separated? I know in granular materials, we do have energy that you have the deformation, you have terms that, 2 deformation modes are together. So.
Yeah, at quadratic order, there's no coupling because of symmetry considerations, right? That there's no way to make a free energy scalar that's a product of these 2 different things with different symmetries. Now, there could be at higher order, right? And that's what you're asking about, right? So if you had the cubic or quartic.
I'm not going to the high order. I'm thinking about, you could have 2 deformation modes that are basically creating one times the others, for example.
No, well, that would be forbidden by symmetry, right? That you can't have 2 different things with the different symmetries and multiply them and get out a scalar.
Up to, as long as you can lose stability at some stage because of that, but you might.
You can lose stability, right? So I think maybe that's the point that you're thinking of, right? That the elastic free energy that I formulated is positive definite in most cases, right? But there can be situations where it's not positive definite, and then it must be stabilized by some higher order terms. I think that's what you're getting at there. And there are experimental examples of that, and that makes complicated situations where the ground state is not uniform, but could have some spontaneous distortion, and you need something to stabilize it.
Yes. Okay.
Great, thank you.
Yes.
For the polar pneumatic, you showed that the compromises could be these kind of circle configurations or cylindrical or so on. But could there be also like the gyroid? There's also a couple of simulations to show that you get a gyroid configuration.
I don't think it would be stabilized by that mechanism.
Okay.
Because this is a mechanism that makes one end different from the other end, right? So this is like spontaneous curvature in biophysics, right? That makes the one side of a membrane to be different from the other side. I think what you want for a gyroid is different from that. It's something that favors having a minimal surface, right, where the sum of curvatures is 0, but the difference of curvatures is non-zero. And that's actually something I've been thinking a lot about recently, and I want to put into my talk next week. But it's it would be stabilized by more like this delta mode,
Yeah.
right? That the delta mode that favors this versus this,
Yeah.
right? That is what would favor a difference of principal curvatures rather than a sum of principal curvatures. And yes, I absolutely think that sort of thing could stabilize the gyro phase.
Thank you.
Any last question? I think we can actually ask questions in a very long tea break. So
Okay,
yeah,
cool.
yeah, everyone is going to rush towards you and use the 1 hour question. I'd like to thank you again and thank